So now that you've got a perfectly inelastic collision in one dimension under control, we're going to try them in two dimensions, which basically means that these two objects strike each other off axis. So just to frame what's happening here, we've got Jim, who has a mass of 20 kilograms, headed at 6 meters per second on an angle that is 70 degrees clockwise of horizontal. And we have Kathy, who is 27 kilograms, traveling at 4 meters per second, tipped 50 degrees counterclockwise from horizontal. And they are going to collide at this particular spot in a perfectly inelastic fashion, which means they're going to fuse together completely and perfectly as a single object. That single object will contain Jim's mass and Kathy's mass for a total of 47 kilograms, and it will be headed somewhere based on how much momentum Jim brought to the table plus how much momentum Kathy brought to the table. So in order to solve this problem, I have to determine Jim's initial momentum, and I have to determine Kathy's initial momentum, and then I have to add them together as vectors, because there will be x and y components in this particular problem. So if we work on Jim first, we'll start with his velocity vector. So Jim is headed this way at 6, and we have a Vx and a Vy. And this angle in here is 70 degrees. Now, you've maybe noticed that when you arrange them this way, and I try to quote the angles from horizontal, and if I do that, then Vx always ends up being the magnitude multiplied by the cosine of that angle. Because if I measure it from horizontal, the x component is always the adjacent side. So Jim's velocity vector, Jim, is going to be 70. Nope. 6 cosine 70. 6 sine 70. And this velocity in the y direction is headed downwards, so I'm going to make it negative. If I render that as decimals, now that I've got this stupid calculator in degrees, cos 70 is 0.342 multiplied by 6 is 2.052. And 70 sine is 0.9396 multiplied by 6 negative gives me negative 5.638. Therefore, the momentum vector would be Jim's mass of 20 kilograms multiplied by this velocity vector, which gives us a total of 20 times 2.052 is 41.04, comma, 20 multiplied by 5.638 is 112.76. Alright, so that's Jim's momentum vector here. That's how much he had when he was on his own as a single object. To repeat this process for Kathy, Kathy's headed this way at 4 with a Vx in that direction and a Vy in that direction and a 50-degree angle measured from the horizontal again. So the x is the adjacent component, the y is the opposite component. So for Kathy, the velocity vector will be 4 cos 50, comma 4 sine 50. And Kathy is headed to the right, so this should be positive, and up, so this should be positive as well. That means that Kathy's momentum vector will be Kathy's mass, so that's 27, multiplied by 4 cos 50, comma 4 sine 50. And if I do all this all at once, let's see, 27 times 4 times cosine of 50 gives me 69.421. And 27 times 4 times the sine of 50 gives me 82.733. All right. Good. So in order to get the momentum that I have at the beginning, so P on the way into the collision would be the momentum of Jim plus the momentum of Kathy. So that means that my momentum headed into the collision is going to be 41.04, comma, negative 112.76, plus 69.421, 82.733. So just looking at these two setups, you can see in the horizontal direction that Kathy has more momentum in the horizontal direction than Jim does. But because they're both headed to the right, these things are going to help each other, right? Jim's momentum forward and Kathy's momentum forward are going to give the new Kajimothy, whatever that says, fused object increased momentum this way. Looking at these second numbers, you can see that Jim's momentum downward is larger than Kathy's momentum upward. So Jim's going to win in this little fight because the downward momentum and the upward momentum are opposing each other. So when I'm done with all this, this fused object should be headed to the right because these two cooperate, and a little bit down because this one is going to overwhelm that one. So, and that said, let's actually do the numbers there. So the momentum in will be 41.04 plus 69.421 gives me 110.431, comma 112.76 negative plus 82.733 gives me 30.027 negative. And the entire theory behind this collision stuff is that the momentum in, as in the momentum before the collision, has to equal the momentum on the way out of the collision, which happens to be, because we're operating under perfectly inelastic conditions here, the momentum of this fused object. Kajimothy. So if I were to take this momentum in vector and set it equal to the total momentum of my new fused object, this momentum should be the mass multiplied by the velocity vector of that fused object. So if I could fill in the 47 kilograms here and divide this side by that mass, I would end up with 110.431 over 47, comma, negative 30.027 over 47 being my new velocity vector. So I'm going to do that. This divided by this and this divided by that. So 110.431 divided by the combined mass of 47 kilograms gives me 2.350 if I round properly. And 30.027 divided by 47 gives me 0.639 negative. So I end up with a velocity that is a great deal forwards and a little bit downwards, which is what we sort of expected. So I have the velocity of this object on its way out in vector form. So I know how much forward it's going and I know how much downward it's going. It would be nice to have that as a combined velocity, so I could just quote you the speed of the thing on the way out. So if I reconstruct that with a triangle, 2.35 this way and 0.639 that way, that's going to give me the full speed if I build it as a triangle using Pythagorean theorem. So my total speed then would be the square root of 2.35 squared plus negative 0.639 squared. And if I work that out, 0.639 squared plus 2.35 squared gives me 5.93, and if I square root that answer, I end up with 2.435 meters per second. All right, so this object here is headed that way at 2.435 meters per second. Lovely. Now you notice that that is slower than both of these two speeds on the way in, and that's due to the fact that the upward momentum and the downward momentum had to eliminate each other a little bit. I'd like to know the angle here. It's always good to have that so that we can quote our velocities in either x and y ordered pairs or magnitude and orientation pairs. So to get this angle in there, to get that, I have an opposite side and I have an adjacent. So that's a tan. Where can I write that? Tan alpha would be the opposite side, 0.639, divided by 2.35. So alpha would be the arctan of, let's see, 0.639 divided by 2.35 is 0.272. And if I arctan that, I get 15.2 degrees. So if I erase all of this math so that I can summarize our results in a sentence, what we've discovered is that the combined object will leave the collision at 2.435 meters per second on a trajectory 15.2 degrees clockwise. Yep. It's been a long day. Clockwise with an S. Trajectory 15.2 degrees clockwise from horizontal. So if you wanted to know the kinetic energy of this particular object, you could pop that number into E equals 1/2 mv squared, and you could get that kinetic energy. So the only thing that's different in this particular problem from what you did in the last section is that when you do the velocity vectors, you're going to have to worry about it having x and y components. And so then when you work out these questions, it net ends up meaning you just have to do it twice. You had to do a momentum in x plus a momentum in x and divide by the mass, get an answer. And then you had to do the momentum in y plus the momentum in y, get a net. divide by the mass, get an answer. And that's how two-dimensional problems really work. The stuff that is horizontal interacts with stuff that's horizontal, and the stuff that is vertical interacts with stuff that is vertical, and never do the two interact with each other. So if you can do it in one dimension, you can do it in two, and if you can do it in two, you can do it in three. We're not going to do that because it's impossible to draw and describe. But just adding dimensions just means you'd have to do the question a third or fourth or fifth time. So there is a second example, I think, in the notes below this video. Maybe not, but you should be set to try the practice problems.